Artificial intelligence is fundamentally based on logical and deductive reasoning. Logic provides the formal structures that make it possible to represent knowledge, analyze information, and derive valid conclusions. Through logical systems, intelligent machines are able to simulate aspects of human reasoning and make decisions in a consistent and explainable manner. The foundations of logical reasoning are rooted in the work of early thinkers who sought to understand how true premises lead to valid conclusions. Logic was originally developed as a method for organizing rational thought and evaluating arguments rather than as a mathematical discipline. Over time, these early ideas evolved into formal systems that could be applied beyond philosophy and into science and technology. Propositional logic plays a central role in formal reasoning by allowing statements to be expressed in a precise and structured form. Logical expressions follow specific rules that determine how they are formed and how they can be interpreted. Understanding both the structure and meaning of these expressions is essential for determining their validity. Logical semantics defines the conditions under which statements are true or false, while logical syntax ensures that expressions are constructed correctly. Logical interpretation methods such as semantic tableau provide systematic procedures for evaluating propositions and identifying logical consequences. By breaking complex expressions into simpler components, these methods allow reasoning processes to be examined in a transparent and rigorous way. Such techniques are widely used in automated reasoning systems and knowledge-based applications. Human reasoning patterns are also reflected in formal logical systems. Everyday reasoning often follows recognizable structures that can be represented using formal notation. These representations make it possible to model reasoning processes computationally and to apply them in artificial intelligence systems. Logical inference techniques enable new conclusions to be derived from existing knowledge in a controlled and verifiable manner. In addition to classical logical reasoning, modern reasoning systems must account for the dynamic nature of real-world knowledge. Non-monotonic reasoning addresses this need by allowing conclusions to change when new information becomes available. This approach more closely resembles human reasoning, where beliefs are continuously revised in response to new evidence. The transition of logic from a philosophical discipline to a mathematical and scientific tool marked a turning point in the history of reasoning. The formalization of logic provided a foundation for rigorous proof and systematic deduction. This development made it possible to establish reliable connections between truth and provability, ensuring that valid reasoning is grounded in verified premises. These logical foundations remain essential to artificial intelligence today. They support the design of systems capable of reasoning, learning, and adapting in complex environments while maintaining consistency, accuracy, and interpretability. Rule-based systems attract considerable interest because of their conceptual clarity and ease of implementation. Their structure is intuitive and closely aligned with human reasoning, which makes them especially suitable for representing expert knowledge in a transparent and interpretable form. These systems rely on explicit rules that describe how conclusions can be derived from given conditions, allowing reasoning processes to be followed and explained step by step. The discussion focuses on the wide range of applications in which rule-based systems can be effectively employed. Such systems are commonly used in expert systems, decision support environments, diagnostics, planning, and knowledge-based problem-solving. Their operational mechanisms are explained by examining how rules are stored, activated, and applied in order to derive conclusions from available facts. Special attention is given to the way inference is carried out and how the reasoning process progresses from known information toward new knowledge. Both forward chaining and backward chaining reasoning strategies are explored in depth. Forward chaining is presented as a data-driven approach in which reasoning begins with known facts and repeatedly applies rules to generate new conclusions until a goal is reached. In contrast, backward chaining is described as a goal-driven approach that starts from a desired conclusion and works backward to determine whether the necessary conditions can be satisfied. The operational logic of each approach is explained along with the general procedures that govern their execution. The efficiency of rule-based systems is strongly influenced by the complexity of rule preconditions and the strategies used for selecting applicable rules. The analysis therefore addresses how complex conditions can affect system performance and how efficient rule selection mechanisms can significantly improve inference speed. A comparative discussion highlights the strengths and limitations of different types of rule-based systems depending on their reasoning strategy and application context. In addition to standard rule-based systems, the discussion extends to alternative reasoning paradigms, such as model-based reasoning and case-based reasoning. Model-based reasoning focuses on using structured models of a system to explain behavior and diagnose problems, while case-based reasoning relies on past experiences and previously solved cases to address new situations. These approaches are examined in relation to rule-based systems to clarify their differences, complementary roles, and areas of application. To support learning and practical understanding, a collection of solved problems is provided along with a comprehensive set of exercises designed to reinforce key concepts and reasoning techniques. These practice materials allow readers to apply theoretical ideas to concrete examples and develop hands-on experience with rule-based reasoning systems. The section concludes with an integrative overview that reinforces the main ideas and highlights the role of rule-based systems and related reasoning approaches in artificial intelligence.